Right. Yeah. All right. So in our second lecture here, we're just going to expand a little bit more. Yeah, ask the questions, interrupt when you're ready. In our second lecture here, we're going to be looking at different ways of how we actually go about analyzing our orders here. With respect to different operations and how do they compound in regards to how we formulate our orders here. Yeah, like I said, if you have any questions, feel free to interrupt. I'll address them accordingly once I see them in the chat. So as I said, feel free to go about interrupting me when you're ready. So if your algorithm is particular, and that's what we're going to be observing here in regards to a code to figure out how do we formulate the order here using this. So in N Runtimes, this is when we have independent loops here that do not nest within one another. So if we have a loop here doing A times of work, and then a loop here doing B times of work, or B chunks of work, the order for this loop alone is going to be O of A, and then the order for this second loop here is going to be O of B. And then when we compound the two to say, okay, for this entire program here, what's the general full order? It's just going to be O of A plus B altogether. That seems very straight and forward and simple, right? So that's when we add runtimes together. You multiply runtimes when you have nested loops. Because the outermost loop here is going to be responsible for the iterations tracked when each case here in B is completed, these two here multiply by one another. And to give you an idea of this, let's say array A here had 3 items, and array B here had 2 items. And we know arrays here, it's going to start from 0, so 0, 1, 2. This is 0, 1. When array A here is at 0, array B here will be at 0, but then it's still at 0 here, and it goes 1. Because that's how the rotations will run. So this innermost loop here must run before the outermost loop here iterates. So the innermost loop must complete all its iterations before the outermost loop iterates by 1. Then we'll go 1 here, 0, 1, 1, 2, 0, 2, 1, and then we complete. And we see here, this is 1, 2, 3, 4, 5, 6 steps, which is basically, if we took these two values here, and we multiplied the two of them together. So, for nested loops, it's going to be that you multiply the orders together regarding each one of these. So, this for loop here, the outermost for loop is going to be O of A. Innermost for loop here is going to be O of B, but because they're nested, multiply the two together. So it's going to be O of A by B or O of B by A. Multiplication, the arrangements of variables don't matter. It's going to be the same thing regardless for multiplication. Same thing with addition, all of the variables don't matter in this case. So the general rules is that so long as your algorithm is like do this, and when you're done with that, you go on to some other operation, you add them together. But if it's that you need to do this for each time you do that, then you multiply the runtimes together. And the nice way of thinking is that if you have for loops that do not nest with one another, so you have a first for loop here and then a second for loop afterwards, they add together. But if you have for loops that nest within one another, then you multiply them accordingly. It's very easy to lose track of this in any sort of interview. Be very careful when you're doing the analysis here. It's also very easy to lose track of any sort of code as well. So do the analysis very carefully when you sort of problem. So there's also dynamically resizing arrays, and in programming terminology, they're referred to as array lists. And they're better than static arrays because, like the name says, they expand and contract with its size. Now, we're going to be observing the order of this when, let's say, an array, let's say, hits capacity and it needs to expand itself. So for this particular instance, let's say the array list hits the capacity and it needs to add another item. We're looking at it, it's going to be creating a new array with double the capacity, and it copies all the elements from the first array list into the new array list. We want to be thinking, how do we describe the runtime of this insertion that actually occurs? That's what we're going to be observing here. Now, this is tricky because we don't know in certain cases if the array was full. So if the array was full, up to n items, for each insertion of the element into the new array, that's going to take O of n time. We also know that when we create the new array, it's going to be twice that of the original size. That's going to be 2 of n. It has to copy those n elements over into the new array. So that means that entire insertion will take O of n time. However, for each one of the elements, note, for each one of the elements, this is going to take O of 1 time. So, in trying to describe all of these operations here, there's a terminology known as amortized time. Because there's a worst case that may happen, but we try to figure out what's going to be our average case. So when you try to incorporate the worst case and the average case, knowing that the worst case will happen at some point, but it will not happen for a very long time or a very long instance, we refer to this as amortized time instead. So let's see what's going to be the amortized time here for our dynamic array for this particular situation. So as the elements are inserted, we can double the capacity of the array, and the size of the array here is a power of 2. We just use this for simplicity's sake, just to explain our relationships here for amortized time. So each time when the array is doubled, it comes like if we had 1, 2, then 4, 8, 16, and we keep on going up to some unknown number x, right? And if we try to sum 1, 2, 4, 8, 16 going all the way up to x, you find that it's going to be a little bit tricky to try and solve that. So what if we did it in the reverse order? See that instead of increasing the array, we downsize the array. It's basically the same thing that we're doing, just in the reverse. Oh wait, it's in reverse. So we'll have like from x, then we go x of 2, x divided by 2, then x divided by 4, then x divided by 8, all the way back down to 1. And it's easier to sum this, because this roughly here is just going to be 2 of x. So, because we know that it operates 2 of x in the reverse, that means going forward, it's going to be operating 2 of x as well. Because it's just a reverse in direction. So, those x of insertions that we saw there, it's going to end up taking O of 2x time. And the amortized time for each insertion is going to be O of 1. So the amortized time for x insertions is going to be O of 2 of x. But for each insertion, the amortized time will be O of 1. Right. Any particular questions regarding this? Amortized time is basically a way for us to describe the average case of your expected runtime of your algorithms, where we also factor in that the worst case will occasionally happen as well. In some cases, your average case and your worst case expected runtimes are the same, but in cases when they are not, we describe this using amortized time instead. This is an instance where the worst case and the expected case do not have the same runtimes, but their worst case will happen occasionally. So we need to describe this using one term, which is going to be referred to as amortized time. All right, any further questions? All right, doesn't look like we have any further questions. Let's move on. Now, we also saw that there was an order of log of n, but where does this order come from? And this order basically comes from when we start looking at what we refer to as the binary search algorithm. So the binary search algorithm is like if we're looking for an x value here and some n elements sorted. Remember, the array here is already sorted. This x element being what we are searching for is compared to the midpoint of the array. So if it's the middle, meaning if it's the same midpoint, we're just going to be returning that. If it's less than the middle, we just search for the left-hand side of the array. And if it's more than the middle, we search on the right side of the array. And we keep on repeating this as we keep on going on until we actually find this x value. Yes, this topic is going to end up coming for a quiz in particular. It actually will be your first quiz. Don't worry, the Wednesday session is tutorials, so we get a lot more practice regarding these topics and regarding how to analyze the code to figure out what's going to be the orders. And next week, Monday, in particular, we also get more practice as well, seeing how we analyze the orders for more complex code and so forth. So I'm not leaving you guys hanging. You actually are going to get practice in the tutorials regarding the analysis of codes and figuring out what's going to be the time complexity for each one of these. So just to reiterate our binary search, if we're looking for some element x here, where we know x is going to be the value, if we compare this to the midpoint of the array, where the array is already sorted from least to most. If it's the midpoint, meaning middle, just return because we already found it. If it's less than the middle, we search the left side of the array. If it's more than the middle, we search on the right side of the array. And we keep on repeating this as we keep on going up. So our example here is like, if x here was 9, and we need to find 9 here in this array of values that's already sorted from least to most. The midpoint here for our array is 11. So we compare x being 9 here to 11, and it's going to be smaller. So at this point, we shrink it down so that we're only focusing on this left-hand side of the array. This here being our left side of array. We choose the next new midpoint here. And we do the comparison. So comparing the midpoint here to our search value, or x value, we see that it's bigger. So then we just only focus on this side of the array instead. Now, we already checked A's here, and we know that, okay, it's bigger, but we only have two values here. So we don't need this part here anymore. We just only compare to the two values. There's only two values here, there's no midpoint. So we just choose to see which one is going to be for 9. And we compare 9 to 9, and we just return to get to our value. So the binary search operates such that it keeps on having the array until it finds its value accordingly as of such. Now, how does this compare back to our of log N runtime? So let's actually observe this. So we started off with that n element array to search, and then we have that n elements, depending on if x was on the left hand side or the right hand side, down to n divided by 2. If we still don't find it, we have that half that we just had it, and we are down to n divided by 4 elements. And we keep on having, going down the road until we stop where we find the value, or we are down to only one element where that absolutely has to be the value. So this is really that we keep on doing a sequence of divisions by a constant factor. So if our array was 16 here, and we divide by 2, it went 8. Divide by 2 again, it went 4. Divide by 2, it goes 2. Divide by 2 here, we got 1, and we keep on going, right? If we did an operation, it's just like if we kept on multiplying by 2, keeping on going up. So 1, 2, 4, 8, 16, and keep on going. So this k expression here to map these multiplications, and then we want to see how we would map it back to divisions, is that where we 2 of k equals to n here, where n is equal to the size of our array. So 2 to the power of 4 here will give us 16, where 16 was the size of our array. And if we decide to write this as a logarithmic formula instead, this is going to be log 2 of 16, which will give us the value of 4 here, our power. So we can say log 2 of n here, because 16 was the size of our array, is equal to k, which maps back to 2 of k equals to n. So whenever you see a problem that where the number of elements are going to be halved each time, this is going to be a O of log N runtime. Conversely, when you see a problem where the number of elements is doubled each time, this is going to be a O of 2 of n runtime instead. I'm just going to write this on the slide for you. So if the number of elements is doubled, there's a chance that it's going to be O of 2 to the power n for your runtime instead. But so what happens if we have different cases where it's not halved, if it's divided by 3, divided by 4, divided by 10, or some other thing like that? For the purpose of our big O notation, it's not important. We're just describing the behavior of the time complexity or the space complexity of our algorithm. And the different bases of the logs just only going to be off by a constant factor. And this is seen by the conversion of logs equation that I'm giving. So if we had log 10 of p and we want to get into some other base, where the other base here is going to be log of 2. There'll be log 2 of p here divided by log 2 of this 10 base that we just know about here. And because of this relationship, because of the conversion of log equations, it's just going to be off by that constant factor once we actually do the calculation as such. So we just keep things down nice and simple. So log 2 of n, or in particular cases, we may say like order of 2 to the power n and so on. But we want to see why we can't do this for powers in the next slide. For logs, we can just keep everything down to log 2 of n or log of n regardless. Oops, no, it's not in the next slide. So the reason why we can't do this for powers is because when you watch the graphs for powers here, be like if it was 2 of n, and 3 of n, and 4 of n, each one of these here, they do not differ by a constant factor. So you can't do this for powers. You still have to specify, you still need to specify if it's going to be O of 2 of n, or of 3 of n, or of 4 of n, and so forth. Or for logs, we can get away with this because of the conversion of log formula here. So you can specify everything back down to O log 2 of n, or you can just say O log of n. That's perfectly fine. But remember, for powers, actually going to have to specify what the power is. 2 of n, 3 of n, 4 of n, and so forth. Because it's not going to differ constantly. So let's go back to our Fibonacci code that we saw in earlier lectures. Let's actually see what's going to be the runtime of this. We're going to go back to our recursive tree here. And basically you saw two function calls here, f of n minus 1 plus f of n minus 1. Actually, this is going to be f of n minus 2. Correct this on the slides. Because that code there is wrong. Correct that accordingly. So you may see those two function calls there, and you think, okay, it's going to be O of n squared. And no, that's wrong. We're actually going to have to analyze the recursive tree here. We saw in our previous lectures to actually figure out what's going to be the runtime or code. So how many orders actually are there in the tree here? Sorry, how many calls are there in the tree? And we don't actually need to count to figure out how many calls actually are going. The reason for this being is that let's just watch f of 2 here. F of 2 here has two function calls, right? And then if you watch f of 3 here, there's 4 and 2. So if we watch f of 4 here, that means it's going to be 8, 4, and 2. What the pattern? So the tree has n depth, meaning the number of levels. So there's level 1, level 2, level 3, level 4. So that's n depth. And each node here has 2 children. And each call here for each level will have twice as many calls as the one above it. So because we just now saw the observation here, where there was 8, 4, and 2, and then 1 here, we see that the relationship can be structured into a table. So we actually observe that pattern here, and if we actually add this pattern accordingly, so I'm going to jump back to the tree here. The branches for each one of these nodes, there will always be 2 branches, and the depth of the tree is the levels at which we're going to be. So if I'm just going to illustrate this, this here is L1, this here is L2, L3, and L4, where L here stands for all levels. So our levels here represents the depth of the tree. So the depth here, in n depth, n here is equal to 4. And we have branches here. So branches equal to 2. And when we formulate our relationship here by adding number of nodes, we get that summation going to be that is going to be order of branches power of 10. So for this case, it's going to be O of 2 to the power of n. So for logarithms, the base of the log does not matter, but however, for exponents, the base does matter. And that's why I just want to explain there. To compare a to the n or 2 of the n or 2 to the n, 3 of the n or 4 of the n, they do not differ by a constant factor. So base to powers does matter a lot when you specify your order. Logarithms, you can just use a standard log, that's perfectly fine because you're just going to define some constant factor. The space complexity of this particular algorithm is going to be O of n. And this is because even though we have O of 2 to the power of n nodes in the tree, for any given time, we only have O of n existing regarding the memory use. So you only need O of n memory available to each one of those particular nodes. Alright, that brings us to the end of our sector lectures, and basically the end of our lectures for today. Are there any particular questions regarding this particular topic that we just saw here? The calls on the tree are each instance of when we have function calls. So remember, this is here when we have f of n minus 1 plus f of n minus 2. Am I correct with this? So these refer to each one of those function calls here because it's a recursion function. So when we go down to f of n minus 1, where we are f of 3, and then when we go to f of n minus 2, we go down to f of 2 according and so forth, as you keep on going. So the calls here are just basically the function calls. I may have dropped there for a little bit. Let me guys know if you're hearing me. If I need to repeat my explanation for the function calls, let me know. Yes, we are doing this basically for the sake of efficiency regarding how fast your algorithm or code runs, as well as how much memory your code or algorithm occupies. This is actually going to be very important when you go into interviews and for any sort of programming that you're doing. So yes, it makes things less time to run, as well as it makes things more efficient using less memory for it to run as well. Right, there were 2 branches coming from each level here because of the nature of our Fibonacci sequence function. Because we had f of n minus 1 plus f of n minus 2 being added all together. So because we had each one of those nodes here coming in. Oh wait, no, this is a modified version. Whoops, sorry. So this actually was correct. Bad. That's why we had 2 function calls. Alright, sorry about that. That's why there were 2 branches coming from each level. Thank you for pointing that out. Right, so because we had f of n minus 1 plus of fn minus 1, we have those 2 branches here for each one of those. That's why when we have f of 4 here, when we return f of n minus 1 plus of fn minus 1, let's say fn was 4, this is f of 3, add f of 3. So we have an f of 3 here and an f of 3 here, of course. That's why we have 2 branches coming from each one of those levels. I forgot that was a modified Fibonacci sequence. My mistake, I'm sorry about that. The explanation also carries along for the actual Fibonacci sequence where it was f of n minus 1 plus f of n minus 2. The explanation is the same thing. But the reason why I had it modified is just to explain those branches from each one of those levels in particular. Alright, any further questions? So the small view of the key techniques you'll need to use is that when you encounter a recursive function in particular, you're going to have to end up using the recursive tree to figure out how you go about finding the order. So once you see the recursive tree expanding in some sort of exponent order, you just need to find out what's going to be the depth of the tree and how many branches each one of those nodes have to figure out what's going to be the base regarding that. Because remember, the order here will follow the general terminology here, O of branches to the power of depth. For the iterative functions, you just basically analyze how the for loops operate. So if the for loops are not nested, but they are following in sequential order, you add the orders accordingly to figure out, okay, if they're going to be O of n, if is that they use independent variables, if like the first for loop was A and the second for loop was B, there will be O of A plus B, accordingly and so forth. If the for loops are nested, it's going to multiply. So if it was n times the outermost loop will run, and then n times the innermost loop will run, that will be O of n by n, which is equal to O of n squared. However, if they use different variables, and there's no relationship between the 2 of them, if the outermost loop was A and the innermost loop was B, it will be O of A multiplied by B. And that's basically the short gist of the techniques that you'll end up using. It's just basically trying to figure out what's going to be the relationship. And once you find out what's the relationship by analyzing the flow of the code, that basically describes the order of your algorithm altogether. So in our particular case, because we saw the tree here expanding in powers of 2, that's how we knew it's going to be 2 to the power of n, where n is the number of nodes or the number of depth. Sorry, and where n here is the depth of the tree. If it was expanded in a logarithmic fashion, meaning that if you had it going in reverse, that we had 8, 4, 2, 1. That's how we know that it goes in a log fashion, because it keeps on having each time. So once you establish your flow of the code here to see how do your function calls operate, as well as how the memory operates as well, with respect to n and so forth, you can basically establish what's going to be your time complexity with regards to big O, as well as you can use the same techniques for the space complexity as well. Now, like I said, I'm not going to leave you guys in the dark regarding this. In our tutorial session on Wednesday and next week Monday, you are going to get practice on example problems to see why it is that we get certain orders in particular, and you will get the explanations and so forth. Now, remember, getting to the final answer is what's going to come towards the marks, your approach. Just putting the final answer doesn't really explain that you understand how it's being done. So if I had to allocate a marking scheme for this, let's say if I gave you a piece of code and I asked you guys to find out what's the order, and if it was worth 5 marks, the final answer is only going to be one of those 5 marks. Your explanations as to how do you derive to the order is going to be those remaining 4 marks. So you can get the final answer wrong, but if your explanation is spot on, you're still going to get 4 out of that 5 marks. Alright, any further questions? Alright, doesn't seem like we have any further questions. So if there are any further questions, feel free to leave them down in the comments down below, or directly email me and I'll get back to you guys accordingly. So just repeating, in Wednesday's session, which is our tutorial session, we'll be doing live practice on particular code problems that you may encounter in an interview, but analyzing what's going to be the time complexity of these particular parts of codes. And we'll also be doing this practice carrying over into next week's Monday session as well. All of these practice sessions that we're doing here is going to be leading you guys up to your first quiz, which is going to be released on next week Wednesday, as well as your first group assignment, which will be released later on next week as well. So, like I said, if you guys have any particular questions, feel free to email, feel free to leave them down in the comments below. You can find a lot of code snippets to practice on to see if you can figure out order of the code. You don't actually need to know particular operations when it comes to like how the functions and things may be run and so forth. You can just watch the general code and you can be like, okay, you're watching the operator with regards to the loops or the function calls, figure out what's going to happen. But Wednesday session and next week Monday sessions, you're going to get a lot of examples to actually practice on. And I'm going to give you guys the code first for each one of the examples, see if you guys can figure it out. And then I'll give you guys the explanations right after we poll and see what's going to be the answers. Alright, so until Wednesday session, take care, be safe, and I will see you guys soon. Later.